it'll be fine until there's that one person that it's not fine
What
for.
if
So
you put it like right there in the middle?
I teach sophomores, and I have my next class is my largest class, and they like bounce into things. I can't risk damaging the school's
So it has
iPad.
to.
Yeah. So I mean, I'm doing the best I can. I could be doing nothing, right? So
Most
If-
teachers don't record their lessons.
Yeah, I'm pretty sure you're the only one.
Okay.
Whose class I have. technically.
I feel like I need this class the most if I'm absent. So,
Yeah.
Yeah.
I'm grateful for it.
well, and I understand that it might be blurry on the screen because it is a whiteboard and we're talking about light reflecting off of a smooth surface. So I do understand, but I'm doing the best that I can to provide you with what I can provide you with. So if nothing else, you can at least hear the conversation, right? So we need to learn about solutions because solutions are all around us. Most of the things that we come in contact with are going to be some kind of mixture, and a lot of them are solutions. So I want to just go through some basic vocabulary. We did this when you were freshmen, but I want to go through some basic vocabulary with you and just refresh your memory of these words. We talked about heterogeneous mixtures, and in a heterogeneous mixture, it varies from point to point within the solution, or within the mixture, excuse me. So, for example, if I were to think about a heterogeneous mixture, what I would think of is like if I go to the beach and I get my bucket and I wait till a wave comes in and I just grab a bunch of water, because mixed in with that water are going to be shells, there's going to be sand, there might be some really small pebbles, whatever. If I look in there, I'm not going to see evenly distributed stuff. It's going to be more like all of the heavy stuff is going to settle out first, and then you're going to have a layer of sand, and then you're going to have the clearish water at the top. That is not the same throughout the entire mixture, therefore it is heterogeneous. It looks different in different parts of it. But a homogeneous mixture is one where it is uniform throughout. Now, uniform means that it is the same. Everything is the same. And when I think of a uniform mixture, a homogeneous mixture, I think of tap water. So if you get a glass of water and you fill it up at the faucet, and you come back and you sit down, you put it on the table, is it going to look the same at the bottom, in the middle, at the top? I hope so, because if not, you need to have a plumber come in, right? That is a homogeneous mixture because even though there's other stuff in there besides just water, it looks the same throughout. Another word that we use for homogeneous mixture is a solution. So homogeneous mixture and solution, those words are used interchangeably, they are the same thing. So in this unit, when we're talking about a solution, we are talking about a homogeneous mixture. Air is a homogeneous mixture. But we don't think about it like that. We don't think of air as a solution because it's not a liquid. They do not have to be liquids. Solutions can be solids, they can be liquids, they can be gases. So the air in this room is a homogeneous mixture. It is a solution. This floor, you see how it looks the same? Here we've got dark blue spots, lighter blue spots, really light spots. Over there, we've got the same kind of random mixture of points. I would consider that a solid solution. Okay, rocks are solid solutions, but they don't tend to be, only certain ones are specifically solutions. Right? Granite is not a homogeneous mixture. You have some chunks here of crystals and no chunks over there. That is a heterogeneous mixture. But there can be some rocks that are solutions. Metal alloys are solutions. So if my ring, my gold ring, it's not pure gold. It is a mixture of different metals to give it strength. There's gold in there too, but there's probably some nickel. There's probably some copper or zinc in there to give it strength. That is a solution. If we would take my ring and cut it up, one piece chemically would be identical to the next piece. Okay? So when we have a solution, there are two parts to our solution. dissolved. And then we have a solvent, and that is what is dissolving. So let's say that tonight I go home and I make myself some spaghetti. Okay? I get my pot of water and I put it on the stove top. What am I gonna put in my water? Before it starts boiling, I'm gonna put salt in there. That's all right, I know what you meant. I put the salt in the water. One, it flavors the water, but two, it also raises its boiling point. We'll talk about that later. So when I put that salt in there and I start to heat it up, do I see grains of salt at the bottom? When you do that at home, do you see grains of salt at the bottom? At first you do. But as it starts to heat up, what happens to the salt? It dissolves. After it's completely dissolved, can you pick out the salt crystals in there anymore? No, we have created a solution.
Yeah.
The stuff that is being dissolved, the salt, is the solute. The stuff that is doing the dissolving is the solvent. That's our water. Now, in some cases, we can have a solvent dissolving more than one solute. Think about ocean water. Ocean water has all kinds of salts dissolved in it, and a salt is a generic word for an ionic compound. So you've got all kinds of stuff dissolved in that water. That's why it tastes super salty when you get a little bit of it in your mouth. It doesn't mean that it's just the table salt, like we just dissolved like one giant block of table salt, like the size of a glacier in the water. There's all kinds of different ionic substances in there. There are multiple solutes in that solvent. Okay? It would be like if I took my pot of water and I added salt and sugar. Salt and sugar would both be solutes, the water would still be our solvent. How do we feel about that? Good? Now, I will tell you one other thing. The solvent is typically the one with the most amount. So if I take water and I take vinegar, and let's say that I add, to my measuring cup, I add 1 cup of water and half a cup of vinegar. Water is my solvent because there's more of it. Alright? But if I take 1 cup of water and I add to it 2 cups of vinegar, vinegar becomes the solvent because there's more of it. Does that make sense? Okay. So, mixtures, blah, blah, blah. Let's talk about soluble and insoluble. Does anybody know what soluble means?
Dissolved into a solution.
Can be dissolved. That's all it means. Soluble means it can be dissolved. It doesn't have to form a solution. It can form a heterogeneous mixture. But it can be dissolved. Insoluble means cannot be dissolved, right? And then we have the words miscible and immiscible. Does everybody know what miscible is? It's kind of along the same lines as soluble, but it's not exactly the same. Immiscible means it forms layers. Immiscible means it forms layers. So, for miscible and immiscible, this is specifically liquids, excuse me. This is specifically for liquids. This terminology means we're dealing with liquids. This means that the two liquids are soluble in each other. Immiscible means that it will form layers. They are insoluble in each other.
Wait, what's miscible?
Miscible is that the two liquids are soluble in each other.
Which one means it'll form layers?
Immiscible.
Okay.
So like oil and water?
Yes.
Okay.
Yep. Salad dressing is a great example here. Now, I don't know how many of you guys use salad dressing, eat salad dressing, make your own salad dressing, but my husband has some health things going on, and I have to make sure that I control how much of salt and all the preservatives he gets. Anyway, so we make our own salad dressing. We just make Italian salad dressing, and we have a glass container, and what you do is you put in water, and then you put in vinegar. And those two liquids are miscible, right? If I put them together, I can't tell one liquid from the other. So those two liquids are miscible. Then you add in the packet of seasonings and stuff, and you mix that up, and then you add in oil. And the oil forms a layer on the top. The oil is immiscible with the water and vinegar that are miscible. Does that help?
Yeah.
So we can shake that all up and get them to mix. But if you look at it very, very closely, what you're going to see are tiny itty bitty droplets of oil that are not dissolved in the liquid. It forms a heterogeneous mixture. Okay? So, I'm not sure what this is. I can't remember. Let's take a look at it, see what it is. Okay, yeah, I don't want to do that today. All right. So let's go ahead and move on. Solvation. Solvation is the process of dissolving. Okay? So let's take a look at the process. This actually might even be the same simulation that I just said I didn't want to do. It is, okay. So let's go ahead and open this up. So I want to tell you that when we are talking about things dissolving, we have to consider polarity of molecules. Polarity, it sucks, I know. Because when the process of solvation occurs, polar molecules tend to dissolve polar molecules. Nonpolar molecules tend to dissolve nonpolar molecules. So what scientists will say is like dissolves like in terms of polarity. Things that are polar, like water, will dissolve things that are polar, like salt. Things that are nonpolar, like, it's not going to be meaningful to you, but carbon tetrachloride will dissolve things that are nonpolar, like, what's a good example? Wax. Okay? So this is inherently tied to intermolecular forces. Like dissolves like. Polar things like to dissolve polar things. Nonpolar things like to dissolve nonpolar things. So, let's take a look at this process of dissolving.
That's water.
Yeah, it's water. And, I mean, I can add the partial charges in here. It's gonna get real ugly real quick though. Oh, that's not too bad. So, water is obviously a polar molecule. Salt, table salt, is not really, it's not a polar molecule, it's ionic. But the fact that it's ionic means that it tends to be considered polar because it's not considered polar. But it acts like polar things because you have distinct charges. Water is polar because it has partial charges. This is ionic, it has whole charges, but it behaves very much like polar molecules do. So let's see what happens when we put this salt molecule in here, or this salt crystal in here.
It's a big thing, salt.
Yeah, are you ready? Watch what happens.
Yes.
And it's gone. It's just off the screen, but I want you to notice, if we look at this sodium ion, what part of the water molecule is near it? The negative side. So that's what happens when something dissolves. The water molecules get in there, and they start to pull things apart. In this case, with an ionic substance, it's going to pull apart the positive and the negative charges, and you're going to get all these negative parts of the water molecule, not 100% of the time, right? Because sometimes there's a little positive one near that. but they're constantly in motion, and you're gonna get the negative parts that are surrounding that positive ion. What do you think is happening to the chloride ion that has now gone off the screen? Yeah, you're gonna have all those those partial positives of the hydrogen are gonna be surrounding that negative chloride ion. And that's how things dissolve. The water molecules get in there because they have such strong intermolecular forces. They're gonna get in there and they're going to force those ions apart. This is how ionic substances dissolve. But the more stuff we put in there, if I put in there 10 of those salt crystals, you're gonna have a whole bunch of water molecules that are dedicated to that one, and they change, like they switch around. You're gonna have a whole bunch dedicated to this one, and a whole bunch dedicated to this one. There is a limit to how much can be dissolved, because you run out of water molecules that can pull things apart. So now let's reset this. We'll put the partial charges back up there, and I'm gonna put in these sugar molecules. Can you see that there are 2 of them there? Here's one right here, and here's one right there, okay? Now I want you to watch what happens, because this is a molecule. Do you see how the water molecules like weaseled their way in there? And they started to separate them? This is what happens with molecules. Because you can't pull them apart, the bonds, you can't pull apart those covalent bonds. But you can get the water molecules between them. And when you do that, that crystal gets smaller and smaller and smaller and smaller until they're separated into just 1 or 2 molecules that are chunks. And you can't see it on this big molecule here, but there are oxygen atoms in there. So this molecule also has some polar portions, and those polar portions are going to align with the polarity of the water molecules. So water is a great polar solvent. It's often referred to as a universal solvent because it does such a good job of dissolving things. However, if this molecule is not polar, how's water going to pull it apart? That's why like things dissolve like things. Polar molecules tend to dissolve polar things. Non-polar things dissolve non-polar things. Any questions about that? Okay, so I'm going to leave this because I think we might have to look at it again. But I'm going to pause it. And let's go back to our slides here. So the other thing I need to talk about with the process of solvation is something referred to as the heat of solution. The heat of solution, it's a thermodynamic quantity. We didn't get to thermo last year. We're going to do some thermo this year. We're going to start with what we would have done last year, and we'll pick up what we need to do this year. But heats of solution, that value tells us the overall change in energy as something dissolves. Okay, it's the overall change in energy as something dissolves. So there are 2 sort of basic categories of heats of solution. The first one is endothermic, the second one is exothermic, and I'm sure you've heard those words before because I used those words when you were freshmen, but this is something we talk about endothermic and exothermic in other classes as you're going through your education. Endo means into, thermal means heat, so we're talking about putting heat into something. Endothermic solution formation means that it feels cold. It's absorbing thermal energy. It's taking heat away from the environment and putting it in the system, okay? Do you remember when you were freshmen and we talked about the absence of heat? When you have an endothermic solution, like if I would mix 2 things together in a beaker and I would have that beaker in my hand, I would be able to sense that it's endothermic because the heat is being drawn out of my hand and put into the solution. I would have the sensation of cold because that means that heat has been removed from my hand. It's the absence of heat. That's what I'm sensing. So endothermic means that it's pulling thermal energy from its surroundings into the solution. Exothermic is the opposite. This feels hot. It's giving off thermal energy. So if I mix two things together, this is very typical of like the hand warmers that people use. As soon as you expose those hand warmers to air, it starts to give off thermal energy. Those are exothermic. They feel warm. So that's the difference. The overall heat changes when a solution forms. That's our heats of solution. Sometimes we have to put energy in to get the solution to form. Like when I need to boil water for my pasta, I need to add heat for all the salt to dissolve. Or exothermic, that when we mix the two things together, it just automatically gives off thermal energy like a hand warmer. Okay? Any questions about that? All right. So solutions don't just always automatically form. There has to be, how do I want to say that? There are factors that affect how quickly solutions form. That's how I want to say it. So let's look at those next. Factors that affect solvation. In order for solutions to form, in order for something to dissolve, there has to be an interaction between the particles, right? When we were looking at that simulation, the water molecules had to get in there and bump into whatever the ionic compound or the molecules that we were trying to dissolve. There has to be a collision. So if we can increase the rate of collisions between the solvent molecules and the solute molecules, we're probably going to get a faster rate of dissolving or dissolution. So if we can increase the collisions, we can get it to dissolve faster. In a lot of cases, not in every case, but in a lot of cases. And if we want to slow down those rates of solution or those rates of collisions, we will get it to dissolve more slowly. So there are a couple ways that we can speed this up. One is we can agitate it. How do we agitate it? Stir it, shake it, right? Not like agitating a sibling. I'm not touching you, I'm not touching you, I'm not touching you, right? Not like that. But stirring it, shaking it, somehow like physically moving those particles around. That's one way, right? Because if you are constantly shaking it, you're constantly mixing up those particles and you're allowing them to interact in a different way more frequently. Surface area. This one's my favorite. Did any of you guys bake?
I'm not good at it, but I
try
can make.
someday.
Okay. So I like to bake, and I'm always fascinated. I'm not a big frosting person because it's too sweet, makes my teeth hurt just thinking about it. But my mom and my mother-in-law both love to make that royal frosting, where you just take powdered sugar, you add a little bit of milk, and you can, add any color you want, and you mix it up. And I love to watch them make it because I'm always fascinated at how much powdered sugar can be dissolved by such little amounts of milk. But it's because and you can't do that with like granulated sugar. It just forms a nasty, gooey, clumpy mess. Yeah. But the difference is surface area. Granulated sugar are fairly large crystals of sugar, and powdered sugar has been pulverized. So there are fewer molecules in that little piece of powdered sugar. But the only difference is the surface area. They're the same substance, it's just the surface area. You can make powdered sugar if you take granulated sugar and you put it in like a food processor or a blender. So what happens is, you just have to stir it a little bit, the powdered sugar with the milk, you just stir it a little bit and it turns into a solution pretty quickly. Because these pieces of powdered sugar are so much smaller than the crystals that there's less there that has to be pulled apart. So the solution forms faster. You've increased the surface area. If I take 3 of those crystals of granulated sugar and what would be comparable to 3 of those crystals of powdered sugar, the powdered sugar is gonna dissolve faster because the interaction between the solute and solvent molecules, there's more surface for that interaction to occur at with the powdered sugar. So it dissolves faster. So, we had this big family get together with like my extended family, and my family's not real big. My mom, her siblings, that family's not real big, but if you go beyond that, it like explodes. It's like an exponential curve. We were having this big get together, and we ran out of lemonade. So my mom was gonna make more lemonade, and she's like, I'm never gonna get this sugar dissolved, because there was ice in the bucket already, and we just added the mix, and we were stirring it up, and I said, add powdered sugar. And she didn't believe me. And now we don't use anything but powdered sugar. Of course, you gotta be careful about the measurements, because they're not the same. But powdered sugar will dissolve faster because of the surface area is greater. Okay? And my mom thinks I'm a genius now, so that's like the bonus, right? Chemistry, who knew? And then the other factor that can affect the rate of solvation, though it can increase it, is by increasing the temperature. But we can decrease the rate of solvation by decreasing the temperature. In most cases. In some cases, it's flipped. So if we manipulate the temperature, we can manipulate the rate. Okay? How do you feel about that? Like it makes some sense? Okay. All right. What time is class over?
In about 20 minutes.
20 minutes? Oh, well, we can't stop now.
Yeah, we can.
I don't think we have time for another slide.
Oh, I think we can do it. I'm thinking 2 more, 3 more, 4,
We got 3.
5 max.
None of these solutions are solving any of my problems yet.
Oh, then we gotta keep going until we get one of these.
No,
Solve your problem.
Courtney.
None of them will ever solve any of my problems.
Hey, you don't know that, we haven't covered them yet.
No.
I wonder sometimes when students say something and then I say something back, if in their head they're going, abort, abort, abort. Right?
Yeah.
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 All right, so in this whole entire process, what we've been talking about is solubility, which is the ability to be dissolved. Some substances have a really high solubility, you can dissolve a lot of it. And some substances have a very low solubility and you can dissolve little to none of it. So we really need to talk a little bit about that. So let's talk, let me see what this is. I really should know, but that's different than the one we just looked at, isn't it?
Yeah.
Yeah.
All right, fine. This is why I always have 50 tabs open on my computer. It's the VLA site timed out. I don't know why there's a dog on it. I think that's weird too. But, yeah, but that there's a dog on that site, I don't know. Shake me, okay. So. Are you okay? Yeah, I don't know, that struck me as funny. Let's start with something that's
Design is so.
easily dissolvable. This is table salt, So, first thing is I want you to look at, see this right here? That's a crystal of table salt. It's ionic, and we know, I know looking at this it's ionic because we have a very geometric pattern where they're lined up, they're distinctly separate ions, and they are lined up in a very neat way to balance out the charges. Now up here, you can see in this table, we've got the sodium ions are the pink ones, the chloride ions are the green ones, and we're gonna count up the dissolved ones, we've got the bound ones. So right now we have 31 of each of those ions in there, but they're bound in crystal form. And the totals here should not change. We should have 31 of each the whole time. So let's see what happens when we let this play out. They all dissolved. Does everybody see that? Now they're no longer bound. There's none bound. and they're all dissolved. So they're separate individual ions bouncing around a solution. The water molecules have gone in there and they've like pulled all those ions apart, and the water molecules are bumping around in between those ions. Good? So let's see how much of this we can add. We've got 115 now.
And they're all matched.
Seriously? Okay. Let's keep going. I am getting aggressive. Uh-oh, I added too much.
No?
No? What? But maybe, I'm
Going
not sure.
slower now.
Blah, 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 blah.
Okay, you added too much.
I added too much. Why are the numbers changing? We have 236 total ions of each type. But look at this, it's bouncing around.
It's trying to unbound them, but it can't because it's.
That's
like-
ridiculous.
Okay, I'm sorry.
Okay.
Not enough water.
So there's a limit to how much liquid can dissolve.
So we just add more water.
There's a limit to how much of the solute can be dissolved in the solvent, based on the amount of solvent that's present. So what we're seeing here, this big clump, that is a crystal. It might not be a single crystal, it might be a bunch of crystals, like a little pile of salt at the bottom of the container, but that's a crystal. At some point, we reach that maximum solubility. And we're there. We're a little beyond that, obviously. So let's talk about this bouncing around here, because this process does not just stop. There's all kinds of collisions going on between the water molecules and this crystal and those dissolved ions and this crystal. And if they come in there and they collide with enough energy, they can cause one of those to pop off, but the solubility is sort of set. So if one of them pops off every now and then, you gotta have one that comes back every now and then. And you're gonna see like, some of these are gonna reform, and then some of them are gonna be dissolved. They're just gonna kinda like plunk themselves together and then float off a little bit. So this process is constantly ongoing, but an equilibrium becomes established. And you're gonna see some of them are gonna come back down to the crystal and some of them are gonna dissolve away. And that's why these numbers fluctuate just a little bit, but they kind of hover around the same amount. It does, and it's kind of soothing sometimes to watch. You can access these on just the internet at home, so if that works for you. Now let's talk about something, let's see. That is maybe not as soluble. This is thallium sulfide. I don't like the colors personally, but
Let's take a look.
that was like totally
That did not-
anticlimactic.
You put too much in, like way too much.
I got excited, I'm sorry. So I want you to compare what you see there to what you see here. Which one has a higher solubility?
Obviously.
Obviously the table salt, because more of it dissolves in the same amount of water. And every salt has a different solubility.
Well, that's not the same.
No, but you can see that it's far less. If we were comparing the same amounts of water, you would see that you'd have less dissolved there. Okay? So do you understand solubility?
Does that say negative 10 to the negative 18 liters?
16, negative 16, yes.
No.
Okay, so let's go back to this. So now, I hope this makes more sense because we just looked at those pictures, right, those simulations. When solvation, the process of dissolving, happens faster than crystallization, then what happens? When dissolving it happens more than crystallizing, the substance dissolves. Okay? When they are equal to each each other, that rate, that's equal to each other. Remember after I added all that extra salt, we saw some pop off and some come back, and pop off and come back? This is in a state of equilibrium. It means that the rate of dissolving is equal to the rate of crystallization. So dissolving and solid formation are happening at the same rate. It's at equilibrium, it's stable. And then another situation is where solvation is happening far less than crystallization. Now, last situation, you have solid formation, you have very little dissolving. And of course, like we just said in the last slide, this is temperature dependent. So in some cases, if we heat it up, you'll get higher amounts of the salt dissolving. But in some cases, if you heat it up, you'll get more crystals to form. There's a difference in the structure of those crystals, the intermolecular forces that are at play, and because of that, temperature is going to affect those systems differently. Okay? Do you guys have any more questions? So I know that Courtney's still looking for a solution to her problem. But we
Not
are
gonna
gonna
find it in chemistry.
You're not gonna find it in chemistry? Are you sure? We can keep going.
No, you just said we were gonna stop.
We are gonna stop because I don't wanna start the next topic on a Friday.
Works
For me, pretty good.
Okay?
Thank you.
Yep, you're welcome. So, I guess I'll give you guys a few minutes to just relax. Yeah. But don't expect it all the time.